This is section 1.3, and we're going to look at a third way of looking at functions. We've seen numerical methods, we've seen looking at them graphically, and we now have an analytical approach. And first of all, in case that's not a familiar word to you, anytime in algebra that somebody talks about doing something analytically, it typically means that we're using algebraic symbols, formulas, equations, things like that. So our analytical approach will be the one where you actually start seeing the formulas rather than just the graphs or the numerical tables of values, things like that. We've already seen that it's really convenient to refer to our functions using this function notation that we've been practicing a little bit, giving the function rule a name, and then also specifying what our independent or input variable is going to be. If I do that analytically or with an algebraic formula, it might look something like this. Think about a simple equation like y equals 2x plus 5. Our independent variable or input is the x, and our dependent variable or our output is the y. Y depends on x because every time you pick an x value, of course, you can calculate y from it. This is a function. Every x value, if you plug in some x, is just going to give you one answer for y. And the rule for the function is essentially take the number and multiply by 2, and then add 5. Now I could rewrite that in function notation by giving this function rule a name. For now, I'm going to say that function rule is called f. I can then rewrite this equation using function notation. My function name, f, it still specifies what the independent variable is going to be, x, and then the output would be our y value, but y isn't explicitly part of this formula anymore. In fact, the y is literally replaced by the f of x. They basically mean the same thing. A couple things. First of all, one more time, we've talked about the fact that f of x is read exactly that way, f of x. Those parentheses do not signify multiplication when you're talking about functions. One other piece of vocabulary that you'll definitely hear me refer to throughout the semester is this input variable is sometimes called the argument of the function, specifies what the input is going to be. And later on, when I start replacing that x with, for example, numbers like f of 7 or something, the argument 7 will tell me what to plug in for the x. So if you hear me refer to the argument of a function, the argument is the input. All right, so let's see what we got here. We've talked about the fact y and f of x occupy the same position. They're interchangeable. And as a matter of fact, sometimes we even write them all together, like this. I can write y is equal to f of x, and then my function rule, 2x plus 5. All right, let's take a look at some of the efficiencies of function notation. If I had the first form, y equals 2x plus 5, and I wanted you to substitute a 1 in for the x, I would actually pretty much have to write that out. Find y when x equals 1. And of course, it's not difficult to do. You just plug the 1 in for the x, and 2 plus 5 gives us 7. But look at how much more efficient I can be with function notation. When I want you to plug in 1 for x, I just substitute 1 for the argument or input of the function. And that tells me the same thing as this entire sentence tells me. Oh, we're supposed to plug a 1 in for the x. And so the process looks the same. We substitute 1 for the x, and get 7. But again, the notation is a lot more efficient. All right, we will be, as it kind of notes at the bottom of this page, using function notation and applications a lot in this course. In this particular section, we're just going to concentrate on the algebraic notation and kind of get comfortable with that, and you'll definitely see more applications soon, just not so much in this section. All right, so in example 1, I have two different functions. F of x equals 2x plus 5, same function we were just looking at. And then here's a new one, g of n. Notice that even if I didn't look at the rest of this, I already know n is going to be the input variable. And there it is. The formula is n squared minus 2n minus 4. All right, we're going to practice evaluating these functions in a few different situations, starting with f of 3. So I'm supposed to go to f, and I'm supposed to substitute 3 for the x. The argument here is 3. So I'll do that. Put in 3 in place of x. And using our usual order of operations, right, we multiply first. And 6 plus 5 is going to be 11. All right, the next one, g of negative 5. So this time I'm going to my g function, and I'm replacing all the n's with negative 5's. So I have negative 5 squared, subtract 2 times negative 5, minus 4. You'll notice that in both cases, when I substituted my number in, did you notice how I put it in parentheses? It's always a good idea, but when you're plugging in a negative number, it's really essential. You won't actually get the same answer if you don't use the parentheses. So I would recommend that in general, when you're evaluating function notation, you just substitute your number in parentheses. All right, negative 5 squared. Negative 5 times negative 5 is 25. And I have a minus 2 times negative 5. So negative, negative makes that a plus 10. And a minus 4. 35 minus 4 is 31. By the way, you're always free to use a calculator for arithmetic. You don't have to do it by hand. In fact, if you wanted to, you could plug in that exactly the way it looks right into your calculator. Now it's also possible to substitute expressions in for the argument, not just numbers. So in A and B, I had actual numerical values to plug into my argument. In C and D, and actually in E and F as well, I have algebraic expressions in the argument. So when I want to find f of a, I go back again to my function f here, and I'm just replacing the x with an a. There's not a lot to really do. Just put that a in for x, and I'm done. Sometimes when you substitute an algebraic expression into a function, there's actually some algebraic simplification that can be done. Let's take a look at D to see that. So this time I'm working with the g function, and I want to substitute 4x in place of the n's. So I'm going to use my parentheses again, just like I was doing before. 4x in parentheses, that's squared, minus 2 times 4x, minus 4. This time, unlike over here where there really wasn't anything to do, this time I can definitely do some simplifying. Just a reminder, when you square something, it means to multiply it by itself. So 4x to the second power really means 4x times 4x, or 16x squared. I can multiply those coefficients, negative 8x, and then the minus 4. That would be a completely multiplied out and simplified answer. I know you've all had some algebra in the past, so I'll just mention if you're thinking, oh, maybe I could like factor or something. Certainly it's possible, but at this stage of the game, I'm not requesting that you factor any answers. You can leave them in multiplied out form. All right, what about E? I'm back to my F function, so I'm going to be looking at the formula for F. And this time I've got 7w squared minus 1 in the argument. So I'm going to be replacing the x with 7w squared minus 1. So I would have 2 multiplied by, using my parentheses again, 7w squared minus 1, and then there's a plus 5. Got a little bit of a distributive law here. Remember that vocabulary from your past algebra? 14w squared minus 2 times 1 is 2, plus the 5. And this time I've actually got a little bit more I can do. I've got some like terms that I can combine. So I'd have 14w squared and negative 2 plus 5 gives me a plus 3. That's as far as I can go, not like terms, so I can't combine them any further. All right, one more of this type of problem. This time I'm going to the rule for G, and I'm replacing the x with 2x plus 3. Excuse me, G was n, right? I'm just going to write the G of n right up here so we can see it on the same screen. There we go. So every place I see an n, I'm going to replace it with 2x plus 3 in parentheses. So first I'd have 2x plus 3 squared, and then minus 2 times 2x plus 3, and then minus 4. All right, again, remember that when you square something, that means to multiply it by itself. So I'm going to write this out. 2x plus 3 times 2x plus 3. And the rest of it I'm just going to copy for right now. And then right here is a structure that I'm hoping you remember from your past algebra classes. You may have used the acronym FOIL, first, outer, inner, last, when you learn how to multiply these kinds of things, or you may have just learned it as 2 distributive laws. However you learned it is absolutely fine. But I'm going to say, starting with distributing the 2x, the firsts will give me 2x times 2x, or 4x squared. I then distribute the 2x to the 3, sometimes called the outers. 2x times 3 is a positive 6x. I then move to the 3, and I'm going to distribute that. 3 times this 2x, the inners, is a plus 6x. And then 3 times 3 gives me a plus 9. Okay. So that binomial times binomial, that FOIL structure, should always give you 4 terms when you're done. All right, I'm now going to distribute this negative 2, negative 4x, negative 6, and then I still have the minus 4. All right, time for combining like terms. I've got the 4x squared all on its own. I then have 3 terms that are x's. 6 plus 6 minus 4. Positive 8x. And then I've got 2 terms that are just constants, just numbers. 9 minus 4 is going to give me a plus 5. Now, depending on how recent your algebra experience is and how much of it you remember, this kind of simplification may be second nature to you, or it may not, in which case it just means that you'll just take a little bit of extra time when you practice these kinds of problems to sort of bring it back. All right. So far, In our example, we've always specified the value of the independent variable, the input value that goes into the argument. It's also possible to be given the value of the dependent variable, the output value, and then be asked to solve for the independent variable. So let's take a look at an example like that. I've got some new functions for us. H of x equals negative 3x plus 7, and k of t equals t cubed. First thing I would like to do is find x if h of x equals 10. So notice, since I'm told that h of x equals 10, I'm going to replace the whole h of x, the output, with 10. So that becomes 10 equals negative 3x plus 7. Now I have to solve a little equation. To get x by itself, I would subtract 7. So 3 equals negative 3x. And then to get rid of the multiplier, negative 3, I would divide by negative 3. And so x is negative 1. And so notice it said find x. That's exactly what we did. We ended up figuring out what x had to be to give us the output of 10. All right, in B, find t if k of t equals 8. So k of t equals 8. I'm going to plug the 8 in for the whole k of t. So that whole side just becomes 8 equals t cubed. Let's see. I would have to take the cubed root. And the cube root of 8 happens to be 2. Again, you're always welcome to use your calculator for arithmetic, particularly like a number like this. If I was using bigger numbers and you weren't sure, plug it in your calculator. No big deal. All right, here's another k of t. I'm going to find t if k of t equals 1,000. So 1,000 goes in for the whole k of t. And that equals t to the third power. Once again, we got to get rid of that third power, so let's use a cubed root. You notice whenever we're doing anything in algebra with an equation, we always do the same thing on both sides. The cube root of 1,000, either you know or you can use a calculator, is 10. So t is 10. Then I have one more of these kinds. Find x if h of x equals negative 15. So h of x is negative 15. I'm going to plug that negative 15 in on the whole left-hand side. And that has to equal negative 3x plus 7. So to get x by itself, I subtract 7. Negative 22 equals negative 3x. And then I'm going to divide by negative 3. And this time the division doesn't come out evenly. I can say negative divided by negative is positive. So one way to express this answer is just x equals 22/3. Or I could give a decimal approximation. I could actually do that division on the calculator, 22 divided by 3. And I could say x is approximately 7 point, it actually is 3333 forever, but I'll round to, let's just say, 2 decimal places. And I could get about 7.33. How you give your answer is going to depend on how the question is asked, right? In some context, you might know, hey, I want one versus the other. But in many cases, whoever's asking the question has to tell you what form they want the answer in. When you do your electronic homework in my math lab, it's going to be really important to read the question carefully, because they may say, give the answer in fraction form. Or they may say, round the answer to 2 or 3 or 4 decimal places. Unfortunately, with electronic things, right, they're not particularly forgiving if you don't give them the answer in exactly the form they expect. So you could do everything right, but if you give the answer as a decimal instead of a fraction, my math lab's not going to take it. So just read carefully and give them the answer in the form that they want it. All right, in addition to finding either the input or the output in a function, functions themselves can have arithmetic done on them. They can be added, subtracted, multiplied, or divided, just using normal rules of algebra. Okay? I want to repeat this caution. I know I sound like a little bit of a broken record here, said it so many times, but remember, the argument of the function is not a multiplier. It simply tells you what value to substitute for the independent variable. So don't try to multiply things by that x or by that number. It's the argument of the function, not a multiplier. All right, let's take a look. I've got actually sort of three similar problems here, and I want to kind of take a look at them and compare them. So the first thing I'm asked to do is for my three new functions, f, g, and h here, I'm supposed to take g plus h of x, not times x, of x. To be on the safe side, I like to rewrite this as g of x plus h of x. Right? I'm just reminding myself that argument applies to both functions. Well, let's see then. G of x, that's 5x minus 4, is supposed to be added to h of x, which is x squared minus 6x. So I'm just substituting each function. I'm substituting the formula for that function. And then I'm going to combine my like terms. So I'm going to start with the x squared. I always like to start with the highest power. I've got some like terms on the x's. 5x minus 6x is negative 1x. I can actually just write that as minus x, right? The 1 is understood there. And then I've got that minus 4. All right, let's take a look at number 2. Number 2 is still g plus h, just like I did over here. But this time, instead of leaving the general argument x, they want me to substitute in negative 1. So since I've already done the work of adding the two functions together, I can actually borrow my answer here and just plug negative 1 in for those x's. So I could take negative 1 squared, subtract negative 1, subtract 4. Notice again, I'm being really careful to put that negative 1 in parentheses as I do this. I'm going to run it through by hand, but you could also type it into the calculator just like that right now. And negative 1 squared, negative 1 times negative 1 is positive 1. Minus a negative makes that a positive 1. Minus 4. 2 minus 4 would be negative 2. All right, just for comparison, I would like to go ahead and ask ourselves, what if I'm asked to find g of negative 1 plus h of negative 1? Is that the same as that? Kind of seems like it should be, doesn't it? Let's do it this way and just see if we come up with the same answer. I'm guessing we will. All right, first g of negative 1. 5 times negative 1 minus 4 plus h of negative 1. Negative 1 squared minus 6 times negative 1. That gives me negative 5 minus 4 in the first parentheses, added to 1 plus 6 in the second parentheses. It's negative 9 plus 7, and there is that negative 2 again. So kind of the moral of the story there is it really doesn't matter if you add the functions first and then plug in your value, or if you plug in the value first and then add them. Works out the same either way. So essentially, what we're really saying here is if you've got two functions, we use g and h, but I'm going to use f and g now, it's okay to plug in first and then add, or to add first and then plug in. They're the same. Okay, so I just rewrote the three functions at the top of the page here, same ones we were working with. And we're going to practice a few of the other operations. We just saw I think it was g plus h. We're going to look at a couple of other combinations and different arithmetic operations. So in number 4, I want f minus h of x. If I want to, I could rewrite that as f of x minus h of x. And f of x is 3x squared. Subtract h of x, which is x squared minus 6x. Notice that particularly when I'm subtracting, these parentheses are really, really important. If I don't put them in there, I won't remember that this negative sign has to be distributed. So I have 3x squared minus x squared plus 6x, which is 2x squared plus 6x. All right, in number 5, we want h minus g of 3. Now I don't have h minus g in general yet, so I think I'll just do them separate. I'll plug the numbers in first this time. I'm going to do h of 3 minus g of 3. All right, h of 3, 3 squared minus 6 times 3. Subtract, and again, notice my parentheses here, g of 3. 5 times 3 minus 4. So I have 9 minus 18. Subtract 15 minus 4 is negative 9. Subtract 11, giving me negative 20. All right, let's try some multiplication. F times h of 2. So again, I like to rewrite. I'm going to go f of 2 multiplied by h of 2. F of 2, 3 times 2 squared, multiplied by h of 2, 2 squared minus 6 times 2 is, let's see, 3 times 2 squared is 4, multiplied by 4 minus 12. This would be 12 times negative 8 is negative 96. Again, I'm running this through. I don't think it ever hurts us to think through the arithmetic, but once you've got the numbers plugged in, as long as you're careful to type in the parentheses, you can type these in your calculator, just the way they look here. All right, number 7, f times g of x. So this time I don't have a number to plug in. I just really want to take f of x and multiply by g of x. Again, I like the rewrite. F of x is 3x squared multiplied by g of x, 5x minus 4. Don't skimp on those parentheses. This is a distributive law. So multiplying here, 3 times 5 is 15, and x squared times x is x to the third, minus 12x squared. All right, we're going to finish up here with a couple of division examples. First one, g divided by f of 0. So I can rewrite g of 0 divided by f of 0. G of 0 would be 5 times 0 minus 4. And f of 0 is 3 times 0 squared. 0 minus 4 is negative 4 on top. And on the bottom, 3 times 0 is still 0. I actually threw this one in on purpose just to remind you. Dividing by 0 is undefined. So this one does not have a good solution. It is simply undefined. All right, I've got one more here. G divided by h of x. Do my rewrite. G of x divided by h of x. And g of x is 5x minus 4 divided by h of x, which is x squared minus 6x. Now I don't have a numerical value to plug in, right? The argument is just the general argument x. So I'm actually done with this one. There's nothing I can do to simplify that. In fact, I won't ask you to simplify algebraic fractions like that till much, much later in the course. So I'm just finished here. All right, that wraps up this section, and it wraps up our look at 3 different ways of looking at functions: numerically, graphically, and now analytically. We'll be looking in the next section at how to put all of that together, and we'll start to apply some nice graphing technology to that as well.